Okay, so today we're very happy to have our final talk of the semester with Eleanor Archer from Tel Aviv University, who will talk about random walks on decorated Galton-Watson trees. Please, Ellie.
Hi, thank you for the invitation, and thank you everyone for coming. If you have any questions at any point, feel free to interrupt me because I might forget to look at the chat. So today I want to talk about random walks on decorated Galton-Watson trees. But before I get to decorated Galton-Watson trees, I actually want to go back in time 100 years and start with this quote, which appeared in Nature magazine in 1905. And the writer is Carl Pearson, who is a famous statistician. And he essentially wrote in to describe a problem in which a man essentially performs a random walk on the lattice, or in particular the 2D lattice in this case. And he wants to know, after n steps, how likely is this guy to be at distance r from his starting point? And nowadays this is well known, but he wasn't sure of the answer. So he posted this problem, and he actually got a reply in the next issue from a scientist, Lord Rayleigh, who said that if you take n steps and you want to look at the density for going distance r, actually the density function looks something like this. And you can see, because of this factor and exponent, really this tells us that if you take a simple random walk on the lattice, then you expect to move roughly square root n steps in time n, because this gives you a decent chance of moving that far. So this is quite well known now, but this all happened in 1905. And since then, we've now started to ask the same question, but on more complicated graphs, apart from the lattice. So, for example, you can also ask the same question if you take a simple random walk on a graph. So this is just if you take a discrete graph, and at each time step you move uniformly to a randomly chosen neighbor of your current point. And so, for example, you can define this on, say, a high-level approximation of the Sierpinski triangle. And if you draw it detailed enough, then actually the distance you would have traveled after time n on the Sierpinski triangle is actually less than square root n. It's n to this power here. So this has now been proved. But also there are some graphs where you may move faster than on the lattice. So for example, here we have a binary tree. And here, because we have a drift downwards away from the starting point, actually, if you start a random walk here, then it will actually move linearly in time. So you can see just from these three examples that you can have different behaviors and different speeds of a random walk on different graphs, depending on the properties of the graph. And you can also, so these three here are deterministic examples, but you can also ask the same question for random graphs. So more recently, people have been considering random walks on random graphs and asking, again, how far should they move in time n? And so here, you can't see it so well, but this is a two-dimensional uniform spanning tree. And it was shown recently that if you run a random walk up to time n on the spanning tree, you actually move n with this particular power. So again, this is less than a half. And the intuition here, and it's similar for the Sierpinski triangle, is that because both of these pictures have fractal properties, this somehow slows the random walk down a bit. So it moves more slowly compared to on the lattice. And in this picture of the spanning tree, just to show you the geometry, you can, the color on the picture changes continuously with the graph, the intrinsic graph distance on the spanning tree. So you can see, for example, this blue bit here is very far from this red bit here in the spanning tree, even though they're close in the original box. As well as spanning trees, you can also ask, for example, about critical Odos-Rényi graphs. And it's known that a random walk on a critical Odos-Rényi graph will move a distance n to the third in time n, roughly.
What did you call that last example? A what? A
critical Odos-Rényi. So if you take G and G.
Okay, I got it. Okay, yeah.
Okay, sure. Yes, and finally, this example, I won't talk about it in detail, but this is a random planar map. And these random planar maps are known to be good approximations for typical random surfaces, in the same way that a simple random walk is a good approximation for a typical random path. And on this particular model of the random planar map, it was shown recently that this exponent here is actually a quarter, so it moves even more slowly than the critical Erdős-Rényi graph, for example. So in general, it's quite hard if you have a graph to understand what this exponent should be. But all of these 6 graphs have nice properties which somehow enable one to do quite specific proofs to understand how a random walk behaves. So for example, with the Sierpinski triangle, you have this nice iterative structure, so you can write down recursive equations. With the uniform spanning tree, there are close connections to random walk paths and loop-based random walks. Actually, this critical graph, this critical Erdős-Rényi graph, this is a lot like a tree, actually, and we understand trees quite well. And then this final result, it's actually a very impressive result, but then there is a nice theory to do with constructing these from random trees, these surfaces. So there are many graphs where we know what this exponent should be, but there are also many graphs where we don't know. And today I'm going to talk about a class of graphs and what we can determine, or the random walk exponent on this particular class of graphs. But before we get to that, we actually need to understand what properties of a graph really affect the random walk displacement and the random walk speed. And in summary, there are 2 main properties of a graph which affect these asymptotics. And the first one maybe is quite intuitive, that it should affect it. And this is the volume growth. So it's clear that the volume growth has an effect. So like I said, in the Sierpinski triangle, because somehow you have quite dense parts of the graph, this somehow slows a random walk down. So you can see that potentially having larger volume will slow you down. But then you could also see in the example of the binary tree, which has exponential volume growth, actually the random walk moves quite fast. So it's also possible that having strong volume growth can actually help you. And really what's happening in the binary tree is that this extra volume is giving you more escape routes to get away from your start point. Whereas in the Sierpinski triangle, these extra volume pockets are somehow slowing you down. But this notion of escapability is captured by a quantity called effective resistance, which maybe you heard about in school. So basically it's a very nice theory. You can imagine you have a circuit, and we know electrons move around circuits, and the effective resistance between any 2 points on the circuit tells you how hard it is for an electron to get between those 2 points. And it turns out that if you view a graph as an electrical network and imagine applying a unit voltage across the graph, then actually electrical resistance is precisely what describes how hard it is for a random walker to get between 2 points. So actually what you have to study to understand this escapability of random walks is also this electrical resistance growth on the graph, if we view the graph as an electrical network. And then once you have these 2 pieces of information, so maybe you have an exponent for the volume growth and an exponent for the electrical resistance growth, the heuristic to understand how the random walk behaves is as follows. So if you take a ball of radius r in your graph around your start point, and you start a random walk, say from point 0, the exit time for the random walk should be of order. Okay, so for example, the expected exit time will be of this order. In most cases, it should be of order proportional to the effective resistance from the start point to the boundary. So for example, in the binary tree where you have lots of paths to the boundary of a ball, this effective resistance is very small, times the volume of a ball. And so this really captures this competing effect of volume slowing you down and also having extra escape routes. And there is a caveat that this just holds for certain recurrent graphs, but this will always be the case in this talk. And so this is the heuristic that we're going to use to understand how random walks behave on graphs throughout the talk. So just as an example to just test this heuristic, we can first look at a critical Galton-Watson tree. So these are now quite well understood. And the thing with random walks is that if you want to understand these exponents which tell you how far you move after n steps, it really makes more sense to study these problems on infinite graphs, because if you have a finite graph, then after some time, the random walk will just mix and everything will converge to equilibrium. So what you really want to do is study this problem on a critical Galton-Watson tree that's conditioned to survive. And the thing is, a critical Galton-Watson tree by itself will not survive with probability 1, but Questions showed that there's a natural way to condition it to survive. And essentially what you do is you just force one single path to survive to infinity. So I drew a drawing of it. So you have a root and you force one path to survive all the way to infinity forever. And then you attach small subtrees to each of these special vertices on the backbone. And all of these subtrees just grow as a standard critical Galton-Watson tree. So in particular, all of these subtrees will be finite with probability 1. And what naturally happens is that if you condition a critical Galton-Watson tree like this to have height at least n, say, then you really just have one path that survives to height n, and you actually create a natural size biasing on the offspring distribution along this one path. Because somehow if you have, say this vertex has k children, you also have k options for which is the next vertex that is on this special path. So actually, if you want to construct a critical Galton-Watson tree conditioned to survive, what you have to do is you have to take one special path of vertices which have a size biased offspring distribution. And then away from this special backbone, all vertices have the normal original offspring distribution and grow like standard Galton-Watson trees. And to understand random walks on this critical Galton-Watson tree conditioned to survive, we have to understand the two quantities I talked about before, which are the volume growth and the effective resistance growth on this critical Galton-Watson tree. Okay, so this is just a repeat of what I just said about the size biasing on the backbone. And it turns out, so in fact, Keston showed in 1986, he showed that if you take this critical Galton-Watson tree conditioned to survive, and by the way, the motivation for considering this was he was looking at critical percolation clusters conditioned to survive. So if you take a ball of radius r, then the volume of the ball is roughly r squared. And the effective resistance to the boundary is also of order r. So the effective resistance to the boundary is, if we're just talking about, on any graph, it's always at most r, because as long as you actually have a boundary, there's always going to be at least one path of length r going to the boundary. But the point is it can be a lot less than r if you have many paths going to the boundary. But on a critical Galton-Watson tree, you really, because it doesn't really naturally survive, you really only have a very small number of paths going to the boundary of a ball of radius r, which means that the effective resistance is actually really of order r. So then if you plug these two things into the heuristic, you get that the exit time from a ball of radius r should be of order r cubed. And then you can just invert this relationship to get the distance to a random walk at time n should be of order n to the third. So this is for finite variance Galton-Watson trees. And you can also play the same game if you have infinite variance, but still critical. And in this case, it's important what your tail decay actually is, because it depends quite precisely. But if you're in some kind of stable regime where the offspring tails decay like a polynomial pile of k, then it turns out that, again, the effective resistance to the boundary of a ball of radius r is still r. And this is for the same reason as before. It's because the whole thing is critical, so you don't have many paths getting to the boundary. But this time, the volume growth is actually, the exponent is a bit bigger. So because you have heavier tails on the offspring distribution, somehow this is causing the volume of the ball to be bigger. And so this time, if you plug it into the heuristic, then you get that the exit time from a ball of radius r is r to this power. And again, you can invert it to get the asymptotics for the random walk at time n. So okay, this is still it's now quite well known, but now the focus has shifted a bit. Now we understand Galton-Watson trees and several other random graphs. One of the current focuses in probability research is to understand random surfaces and random walks on random surfaces. And one approach to do this is through the theory of random planar maps. So I won't talk in detail about random planar maps today. This is just for motivation. But a random planar map is just a planar graph drawn on the surface of the sphere in such a way that no two edges cross. And they're considered up to any continuous homeomorphism and just viewed as a metric space, and we just endow them with the graph distance. So every edge has length 1 in this picture. And in the same way, like I said before, in the same way that a simple random walk is a canonical random path, there are certain models of these discrete random planar maps which can be thought of as a canonical random surface. So for example, here's a simulation of one. So this is a large random quadrangulation. So here all the faces have degree 4. And you can see somehow the geometry of this random surface is very different to the original sphere. So you have all these spiky fractal parts. And this means that you would expect that if you have a random walk on this surface, then it would move a lot more slowly because maybe it gets held up in these fractal parts. And in fact, the result we saw earlier for the UIBT is almost the same graph, but with triangles instead. They showed that the exponent for the random walk there is a quarter, so it really does move more slowly than it does on the lattice, for example. But still, there are lots of, even though a random walk on some graphs in this universality class is now understood and the exponent is known, there are still many graphs or subgraphs of this where we don't know the random walk exponent. So I'm just going to basically just show you some pictures, and I just want to emphasize that in the pictures that in each case there's somehow a tree hiding in the picture. So the first picture I want to show you is, so you can imagine on this graph that you could do percolation on this graph. So you could do side percolation or bond percolation or face percolation. So just for example, say you do side percolation, if you can in fact take a local limit of this graph and condition it to have infinitely many vertices, and you can do side percolation on top of that in the standard way. And as usual, you have a notion of a critical parameter. And it turns out that at criticality, the percolation clusters have very nice shapes and structures. So for example, if you take a large random triangulation, but this looks really the same as the quadrangulation I showed you on the previous slide, and you do critical side percolation. So it turns out that actually the critical parameter is a half in this case. And you isolate one component of your critical, or you isolate one critical component. You can see over here that the structure obtained has some kind of tree structure. So it's not a tree, but you can imagine that maybe if you were to annotate it, draw a vertex in each of these big faces and join them up, you're somehow getting a tree. And it turns out that this tree has a very nice form. It's a Galton-Watson tree, and it has a certain offspring distribution. And then somehow, to understand the cluster fully, you then have to add some information about what's happening inside these spaces. But if you want to understand this cluster, then the first question is to understand what happens when you glue lots of graphs together along a tree structure. So to make this a bit more rigorous, there is a result by Shurian and Kolchemsky, where they proved that if you take this object and condition it to have size n and take a scaling limit, you get convergence to a nice object, which basically looks like a fractal version of this operation done to a tree, but just if you take the boundary of this object. And there are also some nice results by Loic Richier, who says that if you take this object and you take a local limit of the boundary, and then you actually get convergence to a structure we call a loop tree, which is really what you get if you draw a tree like this blue tree, and then you draw loops around all the vertices and join them together. And we know the offspring distribution. The offspring distribution will have stable tails with parameter 3/2. So this is one example. Also, there are other examples too. So this here is a different picture. It's called a stack triangulation. It's completely different, but it's kind of formed in some ways a bit like the Sierpinski triangle. So you basically take a random map and you start with just 2 triangular faces, and then you iteratively split each face into 3 new triangles and keep going and take some kind of limit. And here's a simulation of what you get. And you can see here as well, actually, it looks a lot like a tree. It's not quite a tree, but it looks a lot like a tree. And it was also shown in a paper by Albonk and Marquet that if you take the right scaling limit, then in the right cases, you also get convergence to the CRT, actually, a continuum random tree. So it also has nice tree properties. Here is another picture of an outer planar map. So outer planar random maps are special because they have this property that all vertices are adjacent to some kind of outer face. And there are nice connections to permutations and things like that. You can actually include permutations in these random maps. And they also have a tree structure because you can kind of see, for example, you have big faces like we had before. I won't draw them all. But you can imagine, you can join these spaces along a tree structure and think about what happens to the tree underneath. And this also determines the scaling limit of these maps. And again, this is sometimes the scaling limit can be the CRT, or it can also be something else with more information, depending which regime you're in. And finally, so my final example is an example about quadrangulations. So the red simulation I showed you a few slides ago was a large random quadrangulation. And if you sample a random quadrangulation, say with n faces, its boundary length will typically grow in a certain way. But you can actually force the boundary length to somehow grow linearly with a number of faces. And this gives you a new class of maps. And this P somehow is gives you the parameter. So if you have n faces, then you want to condition the boundary to have a length, I think, a function of P times n. It's not exactly P, but it's a function of P. And depending on how you vary P, you have 2 extreme regimes, but you also have this whole intermediate regime where the boundary of this quadrangulation has this structure where you really have a tree. You can draw a tree underneath this picture, and also the offspring distribution of the tree is known. So these are just a few examples of where if you take nice models on random planar maps, you can get structures that they're maybe not exactly trees themselves, but they're somehow trees with some extra information. And today I want to talk about a class of decorated trees where you take the Galton-Watson tree. So also in all of these examples, I didn't say probably, but the Galton-Watson tree is critical, in fact, the one that's underneath it. And this is somehow coming from the fact that the maps are somehow critical, or the models, the statistical physics models are critical. So you take a critical Galton-Watson tree, you condition it to survive because you want to know about the long time asymptotics of a random walk, so you need to have an infinite graph. And then you assume that really what you've done to your tree is you've kind of joined some blocks along the tree structure in this way. And for example, you can see in this picture that if you were to draw this tree, like if you look at the vertex here, there would maybe be some edges going to these neighboring vertices. And then maybe somehow these are leaves of the tree. But the number of connections to somehow the number of connections to new faces gives the boundary size of this face, and this somehow corresponds to the degree of the tree, the underlying tree that you draw. So the boundary size of this face, if I then draw the tree underneath, the boundary size will be equal to the degree of the vertex in the tree. So I want to define a model where I basically insert a graph at every vertex of a tree, and the boundary size of the graph will correspond to the vertex degree of the tree. So this means, for example, that the graphs I insert will not be independent of the tree. So there's lots of dependence between, even if you sample them independently given the degree, there's still the dependence. Okay, so I'm going to basically define a model which somehow captures this notion. And so I'm taking, when I gave the example of critical Galton-Watson trees before, I said you can look at finite variance or infinite variance. And if you look at infinite variance, then it's important about this parameter alpha, the value it takes. So in this, I'm just going to look at infinite variance today, because actually it turns out if you look at finite variance trees, the model is not so interesting. And really, even if you insert exciting graphs, you don't really change the geometry of the tree by adding these graphs. All the experiments will still be the same as for the original tree. And the ones that really arise in these random planar map settings will be offspring distributions with infinite variance. But we need to fix some parameter alpha, which determines the geometry of the tree and will determine the geometry of our decorated trees as well. So we fix some parameter alpha, which determines the law of the tree. And then we sample a critical Galton-Watson tree, conditioned to survive with this offspring distribution. And then we want to do this operation where we insert a graph at every vertex of the tree and then join the graphs together, a bit like we had in the previous picture. And
what you had in the previous picture, I'm not entirely sure, but it seems to me that the graphs assigned to adjacent vertices had some of their vertices glued together, right? So it's not that they're, I mean, they're sort of gluings, or they're gluings.
Yeah, so you can think, I'm still drawing it. You could think of, you draw the tree, and then each vertex which joins two faces of this big graph corresponds to an edge of the tree. So yeah, exactly. So somehow the two graphs which correspond to adjacent vertices in the tree will be glued together at this vertex, which corresponds to the edge of the tree. So yeah, edges of the tree correspond to gluings of these graphs. Okay. Okay. So yeah, so when I say glue the graphs, I mean exactly that you, if two vertices in the tree are adjacent, then you basically identify a vertex on the boundary of each graph. And you do this in such a way, like in the sensible way, to respect the planarity restrictions. So basically to create the picture I showed you before. Okay, I drew a picture. So this is just for a finite tree. So here is a tree on the right-hand side. So it doesn't really matter what you do with the leaves, because they only have degree 1. So in some way, the graph you sample will just have boundary size of degree 1, but actually it won't really make a difference to the random walk exponents, what you really do with the leaves. So we can kind of ignore them. And so all of these internal vertices, I've inserted a graph, and I've drawn quite different graphs at each vertex. So at this blue vertex, I've inserted this graph. And so for most of the applications, it makes sense to consider planar graphs, but there's actually no reason for what I'm about to present that they actually have to be planar. So you could, for example, have a graph where two edges cross, but you have some ordering on the boundary vertices, which tells you how they should be ordered and identified with these vertices of the tree. And 1, 2, 3, 5, and also maybe I actually can't count, and this should have an extra vertex. But so so basically what's important is that the boundary of this red one, for example, is 5, and this corresponds to the degree of this vertex here. And similarly for the others. Okay, so what do we want to know? We want to understand if we have some, so the graphs we insert in the picture I showed you, they are all quite different, but really we want to imagine that we're sampling from a whole family of graphs, and they may be random or deterministic. So you could, for example, insert a complete graph at each vertex, or you could, what I'm more interested in what happens when you sample a random graph. And what we want to understand is, if we know a bit about this family of graphs that we insert, can we understand what this random walk exponent is? And this is just a fancy way of saying that if you look at the distance you've traveled up until time n, then it grows like n to this exponent plus a to the power of 1. And we'll do this by considering the volume growth of these graphs and the resistance growth of these graphs. So actually, if you know about random walk exponents, we actually determine the full set of random walk exponents, so the spectral dimension and the walk dimension, etc. For today, I'm just going to mainly focus on this displacement exponent because I like it more, but we actually will get the full set of random walk exponents. But in order to do this, we have to make, so I said that for the tree, there's a parameter alpha, which is the offspring distribution of the tree, determines the offspring distribution. But we will also have to make some kind of assumptions on the graph we insert, the family of graphs. The first, I will just give you a bit of notation. So what we're really interested in conditioning on when we insert these graphs is the boundary length of the graphs, because these corresponded to the degree of the tree, the degree of the vertex in the tree. So GM will just denote one of these graphs which has n boundary vertices. It will also be important. So for example, in the pictures, you can see that because we had this, in this critical Galton-Watson tree, we had this special backbone, which is the one path that survives to infinity. We will want to know, for example, how distance adds up along this backbone. And it turns out that basically, well, I guess it's natural that the child, if you take a vertex on this backbone, the child, which is the next backbone vertex, will be uniform amongst the children of that vertex. So this somehow, in the graphs we insert, this somehow corresponds to looking at what happens between two uniform points on the boundary of these graphs. And so understanding how distance grows along the decorated backbone of this tree, the decorated tree, we have to look at how distances add up between two uniform points on the boundary of the inserted graphs. And also, okay, so we're mainly interested in things to do with the graph metrics. So dm will just be the graph metric on gn, sorry. And we will look at this distance between two uniform vertices a couple of times. And then the second thing that I said we had to look at is the effective resistance. So similarly, we'll also let R and U denote the effective resistance between these two boundary vertices. And most of the rest of the notation is self-explanatory. So we'll also be interested in the diameters of Gn and the diameters with respect to this resistance distance. And the volume of Gn is its volume, but in particular the number of edges, as opposed to the number of vertices. And so, I mean, actually I have the formal assumption, but really I think what you should keep in mind is the bits written in red. So we need to assume something about the family of graphs we insert. So we basically assume that there are three key exponents basically, which tell you how the graph distance, the resistance, and the volume add up across the graphs we insert. So then the aim is, once we've got these three exponents, plus we have the alpha from the tree, the aim is to then write the random walk exponents in terms of D, R, V, and alpha. And you do need to have some assumptions on the tail decay. And this is mainly because what you want to say is that somehow the big graphs you insert will correspond to high degree vertices in the tree. And if you have really heavy tails on your, say, the volume of a graph you insert, then maybe this won't be true anymore. So basically you need some assumption on the tail decay so that big graphs really correspond to high degree vertices in the tree. And in some regimes, this is not completely optimal, but you do need some kind of polynomial tail decay. So yeah, and if, for example, this final assumption is not true, or say, at least if it's not true without the epsilon, then really you kind of somehow lose, the tree structure doesn't really tell you anything after this point. And so you have these three assumptions, but really it's just these three exponents which tell you how the distance, the resistance, and the volume grow across these graphs, and how they depend on the the boundary length of the inserted graphs, which is going to really be the degree in the underlying tree. And just to give you the big picture before we dive into some proofs. So I said the diameter of the graph is n to the 1 over d. So if d is small, this means somehow that these graphs are more spread out. So maybe you're changing the geometry of the tree more. And again, with the volume, clearly if V is big, then it means the graphs are quite dense. So again, maybe you're having a bigger impact on the geometry of the tree. And in terms of, if you just think about the metric space structure for a minute and ignore the volumes, it turns out there are actually two main regimes for what can happen. So basically you can insert graphs that are not too spread out, and then actually they won't have much effect on the exponents for the tree. So you kind of have a tree regime if D is big enough. And if D is small, on the other hand, then this means that the graphs are spread out, and then you can actually really affect the geometry, and really somehow the local graph geometry dominates. So in the tree regime, you would expect that you can take a scaling limit as a metric space, and you would just get a tree, a fractal tree. Whereas in this graph regime, if you take the scaling limit, you should really get some kind of tree of graphs persisting, and this is being looked at by some people and should hopefully be released in a forthcoming work. So yeah, maybe I can try to explain why these exponents, or why the threshold is here. So really we have to understand, if we're going to understand what affects the geometry of the trees, we have to understand the volume growth first, and secondly, the resistance growth. And so you can actually, before we jump to these decorated trees, we can actually just take an argument for critical trees with no decoration, just the trees themselves, and understand the volume growth of these. And then we can adapt the argument to understand the volume growth of the decorated trees. And basically the one theorem, I mean, I can write it formally below. The one theorem I'm going to use many times is to add up lots of random variables with stable tails. And in particular, we're mainly going to be in the regime where, well, often going to be in the regime where P here is less than 1. And in this case, if you add up lots of random variables with these heavy stable tails, then both the maximum and the sum of them will be of order n to the 1 over P. If you have P being bigger than 1, then you're more in a lot of large number settings, so they will differ.
What's this notation with the sort of 10 shape? P 10 to 1?
Oh, this notation here.
No, a little to the right of that. There's a P something. What is that?
Sorry, just the minimum, sorry.
Okay, sure.
Yeah. So yeah, if P is less than 1, then it's n to the 1 over P. If P is bigger than 1, then it's just n. And okay, I was being a bit vague about what this one here means, but if you want it formally, it means that if you take lambda to infinity here, then these probabilities will go to 0. And this is the maximum. Okay, so we will just apply this theorem, maybe like to prove all of the theorems basically. So how do you get some intuition on the volume growth for just the tree? So what you want to do is you want to take the ball of radius r. So you can first look at distance r along this special backbone, which has these special size bias vertices. And then, okay, I said that the offspring distribution is size bias. So the stability parameter for this backbone is actually alpha minus 1, which is less than 1. So from the previous theorem, we immediately get that the total number of offspring emanating from this backbone just at the first level, i.e. the green vertices, is really of order r to the 1 over alpha minus 1. And then what we have to think about is then what happens to the subtrees that we attach here. So this is a nice fact. So you can prove it, for example, by looking. So actually there are ways to code, I don't want to get into it now, but there are ways to code random trees through random walk excursions. So you can get these two asymptotics here from looking at asymptotics for random walk excursions. So for example, this is somehow the length of a typical random walk excursion. And so you have some nice asymptotics for the volume and the diameter of these subtrees which are attached. So if you want to use these, firstly, what you can say is that just from what I said on the previous slide, again, this exponent here is less than 1, because maybe I didn't say, but alpha is bigger than 1. So this means that if you take the maximal subtree, so we have 1 over alpha, so then we have to then raise this to the power alpha to get the volume of the maximal subtree. And similarly, we raise this to the power alpha minus 1 to get the maximal diameter. It means that the maximal subtree has volume of this order and diameter precisely of order r, which is the volume, the radius of the ball that we're interested in. And because I also said that when these exponents are less than 1, actually the sum is of the same order as the maximum, what this really tells you is that actually the volume of the whole ball of radius r is really of this order. So this is one way to deduce that the volume of the ball of radius r in the undecorated tree is alpha over alpha minus 1, r to the alpha over alpha minus 1. But okay, we're not interested in the undecorated trees. We actually want to think about what happens when we add these extra graphs. But we can actually play the same game. It's a bit more complicated, but actually we just applied the previous theorem about these sums of stable variables several times. And so the first thing to note is that, I can annotate it again. If you look at the distance, so if you want to take one of these special background vertices and you want to know about the distance from, say, this point to this point, we said that the distance, or that this distance is roughly the degree of the vertex to the power of 1 over d. So this probability is precisely not precisely, it's roughly the probability that the degree to the 1 over d is greater than x. And we said that we have alpha minus 1 stable tails now, so this should decay like x. If we put the d over here, x to the d to the power of alpha minus 1, because we have the size biasing. And also by exactly the same argument, if you take an internal vertex, so here I mean a vertex somewhere over here, again, we have, you can just compose the relations and you get the probability that the volume of one of the graphs inserted at a typical internal vertex decays with x to this related power. So instead of d, we have 1 over v. And instead of alpha minus 1, we have alpha because there is no size biasing on the internal vertices here. And then you want to, if you want to repeat the argument from before, we actually want to know about a whole subtree. But then we can still just actually use the same logic as before, because if we have, for example, for the volume, if we have this relation, then I know that if I have a critical Galton-Watson tree, say with n vertices, and I want to know the volume of it, then I'm roughly adding up the volumes of n of these graphs, like this. So according, again, to my theorem about sums of stable random variables, if I have n of them, and this is the exponent, then the sum will be of order n to the 1 over the minimum of this f, minimum 1. So then if I want to look at the probability that the subtree I attach has volume at least x, then it's roughly equal to the probability that the volume of the undecorated tree is greater than x, but to the inverse of this power, so f alpha v minimum 1. And I said on the previous slide that this is known, and you basically then just divide this by alpha. We had 1 over alpha. So by composing these relations, you get that for one of the overall probability that one of these attached subtrees has volume greater than x decays like this. And for the diameter is a bit harder to prove. I mean, you can prove a lower bound by the same argument, but actually it turns out that actually you can also prove an upper bound for the diameter by the same logic. And here we just have the alpha minus 1 instead, because it's coming from the, you have to think about the worst parts of the tree, which also have some size biasing. But so basically you just have to do the algebra and everything drops out. And then once you have this information, we can proceed as before. So, okay, I just rewrote the same information just further up on the screen. And just to remind you, these are what the exponents are. And then what we want to say is you want to say we just go distance r along the backbone. And now the total number of green vertices or subtrees that we have to consider, rather than r to the 1 over alpha minus 1, we have this extra power of this exponent, minimum 1, which is coming from this power here. And then, again, then we have these subtrees. The probability that one subtree is bigger than x decays like x to this power. So then we just take this power and divide by this power, and we get the overall power for the volume of the maximum subtree. And also similarly for the diameter, we actually have the same power here and here. So they cancel, and we get that the maximum diameter is also of order r. And once again, these exponents are heavy-tailed, or the exponents are less than 1. So actually, okay, maybe not this one, but for the volume anyway, the exponent is less than 1. So this means that actually the maximum gives you the sum as well. So actually, this really tells you that the exponent for the ball of radius r for the volume is precisely this exponent here, which looks quite horrible when you look at it. But really, what's happening is that if you were to just look at the tree, well, we did just look at the tree, and we said that the exponent for the tree is alpha over alpha minus 1. So here, what we've done is we've basically had to introduce these extra 2 factors which weight the exponent, and they basically reflect how distances add up differently along the backbone, which is the top factor, and how distances, volumes add up differently inside the fragments that are attached. And somehow, the reason we were taking a minimum 1 all the time, well, maybe not the reason, but this somehow corresponded in the first theorem. It kind of corresponded to the finite mean case, where you have law of large numbers behavior for sums and things, and the kind of the distinction between this and then a heavier tailed case where you have maximums dominating. So it doesn't look so nice, but actually you can draw a picture of what this exponent looks like. Okay, so basically because there's some transition depending on D and some transition depending on V, it's not clear which one will tip first, and either of them can tip first. But in general, when both of these are greater than 1, then actually you just have the same exponent as for the tree, and you have this tree regime. And when they're both less than 1, then you actually really lose the dependence on the tree. You actually just get VD, there's no alpha. And this is what the graph regime. And in this graph regime, you will just see basically, or really all you see is just having a sequence of graphs glued in a line along the backbone, and the fragments don't make so much difference. Okay, so this was the volume growth, and you can write this in the theorem if you want to write it formally, but basically, if you want to say something almost surely, then you will actually have logarithmic fluctuations around this quantity. But for example, the probability that this volume is between epsilon times r to this power and epsilon inverse times r to this power, this will go to 0 with epsilon uniformly in r. And okay, so I said this before, basically you have these 2 regimes. You have a tree regime and a graph regime. Okay, so you can play the same game for resistance, but it's exactly the same argument. And in fact, the argument I showed you, well, okay, I said to you, maybe I can just repeat it quickly. To kind of understand the effective resistance, I already said that if you go distance r along the backbone, then the number of subtrees with height at least r is really, well, the maximal subtree will have height of order r. And also it's a fact that the number of subtrees with height at least r is an order 1 random variable. And this is coming just from plugging in the fact that you have the same exponent here on the x compared to the number of vertices you have. So what this means is actually, if you want to count the number of escape routes to the boundary of a ball of radius r, actually like the number of disjoint escape routes is really a random variable of order 1. And so it really means that actually you have to, the effective resistance to the boundary of a ball of radius r is really r, actually. It's not smaller than r. And actually the same logic works on the decorated trees. And again, you can just do exactly the same game as we did before of counting. And if you now, rather than, because we just changed the metric to the resistance metric rather than the graph distance, we have an r here instead of a d, but actually r plays exactly the same role as d. And if you were to just count how many of these green vertices you need to have to go distance r along the backbone in terms of this resistance distance, you have the same expression as before, but we just have r in place of d by exactly the same argument. So this tells us actually that the number of subtrees with a resistance diameter of order r is exactly an order 1 random variable, which again tells us that the number of paths to escape from this ball is really somehow order 1, and the resistance to the boundary of a ball, a resistance ball of radius r, is also r. And so then you can just combine these together. You can do some algebra, and then you get these really horrible expressions for what the exponents are. And so you don't have to look at these in particular, but again, the point is that for the tree, you would just get the same things, but replacing all of these brackets with 1. So for the tree, this one, the one that we're interested in was alpha minus 1 over alpha minus 1 plus alpha. And then we just, again, got these different weightings, which kind of reflect how different things add up differently along branches and in subtrees of the tree. And again, you can write some theorems to say it formally. For example, if you want to know about this, the distance you've reached up until time n, it's really n to this power. And again, you have some logarithmic fluctuations. But if you just want to, for example, rescale this by n to the inverse of this power, then you have tightness with this random variable. And you can also, there are standard results which allow you to then say something about the transition density. And the transition density will grow like this, but there are really just standard routes. Once you have the volume and the resistance to go to get this exponent or the spectral dimension, if you know what that is. But yeah, so the main thing is establishing these volume and resistance exponents. And there are also so many results. So you can take expectations as well. In general, to take expectations, you only get lower bounds because actually it turns out that in the original tree, because you have this size bias bound on the backbone, for example, then the volume of a ball actually has infinite expectations. So you can't, in general, get upper bounds on all these expectations. But what you can get is if you, for example, raise this to a power gamma, where gamma is small enough, then you can get an upper bound, which is this to the gamma, but just with a plus here. And just to finish quickly, I won't go through all the examples, but here are just some examples of graphs you could insert. And so you can think of inserting random trees with different parameters. You would hope that when you insert a star like this, you should recover basically the original tree model, and luckily you do. The loop tree is the extreme example where you actually insert a cycle of length n at the vertex of degree n. And this somehow corresponds to the boundary structure of these random planar maps with these structures. One thing is quite interesting, you can insert, if you do a bit of surgery to Sierpinski triangles, you can insert these. And these also satisfy the assumptions. And although it's a bit of a contrived model to insert Sierpinski triangles, it's known that if you look at critical percolation clusters, for example, they really have fractal properties. And so the fact that the Sierpinski triangle satisfies the assumptions, because actually the assumption, it did say something about somehow the diameter of these graphs being comparable to the distance between two uniform points on the boundary. So the fact that these fractal graphs satisfy the assumption gives hope that things like critical percolation clusters, an example I gave before, would also satisfy the assumptions. You can be plugged in, and you can basically also insert dissections if you're interested to recover outer planar maps. And so yeah, it's not particularly interesting what the value. Here's a Sierpinski triangle. these precise values aren't particularly important, but the fact that you can actually plug them into the model is quite nice and encouraging for the percolation cluster, and also for other critical, like for example, some FK models also fall into this framework, so also encouraging for other critical statistical mechanics models. But yeah, I will finish there. So thank you everyone for listening.
Thank you very much, Eleanor. Are there any questions or comments? So Eleanor, I wanted you to go back a few slides, maybe to where you explained the intuition to those formulas with, like you explained that the alpha over alpha minus 1 is the basic the basic exponent you would expect. And then yes, this exactly, I think. Like so why intuitively is this correction with S and F again? I think I missed that.
Yeah.
Seems to be a good point.
So like in the tree, somehow the alpha minus 1 is coming from the fact that the number of these, if you go distance r, is r to the 1 over alpha minus 1. And then the alpha is coming from the fact that you have this alpha here on the volume tails. But now if you have a different metric, then basically the number of vertices you have to explore, if you have a different metric, but you want to go r in the different metric, then the number of tree vertices you have to explore will actually be, here it is, will actually be this number. So rather than, so it will depend on how the metric grows. So before we had r to the 1 over alpha minus 1, but this is telling you how this new metric grows. So you would explore fewer tree vertices, which affects how many subtrees you see.
I see. Okay.
So this is why the first parameter appears, and equally then once you know how many of these subtrees appear, then you want to kind of look. It turns out you just need to look at the volume of the maximum one. But again, now you've added these extra graphs. The volume tails for the inserted trees, they don't decay like 1 over alpha anymore. Instead, we have this extra factor. So before we had x to the minus 1 over alpha for the tree. But now we have this extra factor because we're getting, so if the volumes of the inserted graphs are very heavy tailed, then if you have a tree of size n, then the total new volume of it will be n to the 1 over this power, the inverse of this power. So somehow also you're adding up, you're getting more from each subtree as well. And this is why this factor appears.
I see. What was V? Remind me.
V, so the volume of Gn should be like, with high probability, it should be of order n to the V.
Oh, okay. 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 I see.
I have a question, Ellie. Thanks for the talk. So could you say again which models for random planar maps and processes on them, like critical percolation, give rise to this sort of decorated Galton-Watson trees? And your results imply for these processes additional facts?
So yeah, I think the main example is critical percolation, or the main example I'm interested in.
Yes.
But so to understand what happens on the critical percolation cluster, you obviously need to know you need to check that the individual blocks verify the assumptions. And at the moment, this is not known. And I think it's quite hard.
But it is of this form. It is exactly a decorated Galton-Watson tree, but the assumptions are not verified.
It's known that the boundary, for example, is exactly what we call a loop tree. And it's known that you really do have a Galton-Watson tree underneath, and also the alpha for the tree is known. But what really happens inside the blocks is the exponents are not known, or maybe the volume one is known. But the resistance is actually the really hard thing to understand on these, I think. But it's actually not just critical percolation, so also can't remember exactly which regime, but in several regimes of the FK model, you would expect the same thing. And actually, there should be like a whole class of critical statistical physics models, which somehow, I don't know, like anything that corresponds to a stable map in the right regime should somehow have one of these tree structures.
Okay, thanks.
So actually lots. The example is there should be a whole spectrum. Also like ON loop models, for example.
Which models?
Some ON loop models.
Yes. Thank you very much.
Can I just have a question, sort of thinking out loud? There's a new literature that is sort of still in its infancy of random walks on simplicial complexes. So this would be like you have your triangulations and quadrangulations and so on, but your walks are really along the edges from vertex to vertex. Okay.
Yeah, my walks are.
Right, but these walks go from, say, if you had a quadrangulation, you would be walking from one square, right, to another square or so on. And if you had simplices, you'd be walking from, you know, a tetrahedron to another tetrahedron via the sides and so on, right?
Okay.
So there's a literature that is starting out and asking the same sort of questions that you asked about random walks. But just looking at the pictures of quadrangulations and so on, I wonder if these decorated trees, right, wouldn't be a tool to work there. So
So I think these decorated trees tend to arise very naturally in the planar setting. So depending exactly what your graphs
this is a high dimensional setting. The planar setting, I say.
So maybe, I mean, in high dimension, it's still possible. It's still possible, but it's not clear to me that it would necessarily be a Galton-Watson tree.
Okay.
But it's possible. I don't know, to be honest. So often in the planar setting, you can do some kind of nice exploration of the boundary of some structure, and because you have planarity, you have a natural order for exploring things, and this makes things simpler. And also with Galton-Watson trees, you normally have some planar embedding, but yeah, I don't know if you have higher dimensional things, whether you still get the same.
Thanks.
But
nice talk, by the way.
Thank you.
Okay, so let us all thank Eleanor again, and thank you all for participating throughout the outbreak and crisis, and I hope that next year will be more normal, but anyway, enjoy yourself until then. That's the final meeting for this year, and stay tuned. See you all.